Welcome to iLecture and here's another great example of how we work with Faraday's law and Lenz's law. The example here is a conducting wire that's shaped in a U-shape or horseshoe shape. At the end we have a resistor and we have a bar that is able to slide back and forth across these, you can call them rails. And there is a magnetic field through this loop. It's directed into the board. The strength of the magnetic field is 0.8 Teslas, and we're going to move the bar to the right at 2 meters per second. The length of the bar from one end to the other end between the two wires here is 1.2 meters. And the kind of questions we could ask are, what is the EMF induced? Because of the increase in the flux, as this bar slides to the right, there's more and more flux through the loop, so there's going to be an EMF induced. That's going to induce a current. So what is the induced current? What is the direction of the induced current? What is the power consumed by the resistor? How much force is required to move the bar to the right? And finally, what is the power required to move the bar to the right? So this is a very interesting and very revealing problem because it'll show you a lot of the information that you need to know regarding Faraday's law and Lenz's law. So starting out, let's figure out the EMF induced. So the EMF induced is equal to minus the change in the flux over time. And of course, we know that the flux is simply the product of the magnetic field times the area of the loop. And you can see that the area is perpendicular to the magnetic field. So this is equal to minus delta B times A over time. And in this case, the magnetic field is not changing. It's the area that's changing, so the B can come outside. So this is minus B times a change in the area over time. And of course, the area of this loop is equal to the length times the width. And so we can call the length X and the width L. Well, it's not traditional, but that works for us. So minus is equal to minus B times a change in the L times X over time. Now I'm moving over this way. Now you can see here that the L will be a fixed value. The distance between the lines here doesn't change, so the L can come outside. So this is minus B times L times the change in X over time. And of course, the change in X over time is the same as the velocity. So this can be written as minus B LV. And I'm plugging the numbers that they're equivalent to. We have minus the magnetic field strength, which is 0.8 Teslas, times the length, which is 1.2 meters, and times the velocity, which is 2 meters per second. And all that together will give us an EMF of, my calculator, so 0.8 times 1.2 times 2 equals 1.92 volts. It's minus. The minus simply indicates that it will create an EMF that sets up a current, which is in opposition to the change of the flux that caused it in the first place, which is, by the way, Lenz's law. All right, so now we have the EMF induced. Next thing we're going to do is find the induced current. And using Ohm's law, I induced is equal to V over R. In this case, the voltage that causes a current to flow through the loop is the induced EMF. So in this case, it's equal to minus 1.92 volts divided by the resistance of 5 ohms. And what is that equal to? Divided by 5 equals, it is 0.384 amps minus, again, the minus means that it's going in the opposite direction of the magnetic field that induces the current. All right, next item is the direction of that induced current. Well, for that we have to understand Lenz's law. And notice that we have a magnetic field which is into the board, and the magnetic field flux, the flux will be increasing as the bar slides to the right, the area will be bigger, so the flux is increasing. Flux is increasing, which means that that increasing flux will set up an induced EMF, which will cause an induced current, which sets up its own magnetic field that opposes the change. So since the flux is increasing, the induced current will set up a magnetic field opposing that increase. To oppose the increase, it'll set up a field in the opposite direction. So the induced B field will be out of the board. That's B induced. And then using your right hand rule, take your thumb, point in the direction of the induced B field, and your fingers will curl in the direction of the induced current. So the induced current will be like this, I induced, counterclockwise direction. All right. So Direction of I will be counterclockwise. Next, we now have to find the power consumed by the resistor, and power consumed by definition, that is equal to I square R. The current through the resistor is 0.384 amps. We have to square that and multiply times the resistance of 5 ohms. And what do we get there? So square this times 5 equals, and that would be 0.737 watts. That's the power consumed by that resistor. Now, how much force is required to move the bar to the right? Well, that force will be needed to overcome the force that's on the bar in the first place, because there's a current flowing through the wire. The current is going this way, and that will cause a force. The force on a current-carrying wire is equal to I times B times L. In this case, the current is 0.384 amps. The magnetic field, 0.8 teslas, and the length exposed to the field will be 1.2 meters, 1.2 meters. And that will cause a force on that bar. So 0.384 times 0.8 times 1.2 equals, the force is equal to 0.3686 newtons. Keep a couple of extra significant figures so I don't have a round-off error. So what's the direction of that force? Using my right-hand rule, point my fingers in the direction of the current, then I curl my fingers in the direction of the magnetic field, and the thumb will point in the direction of the force. So the force on the bar is to the left. That's the force. And of course, in order to cause the bar to slide to the right at a constant velocity, I have to apply a force that is equal in magnitude and opposite in direction to move the bar. So I need a force equivalent to 0.3686 newtons, pushing the bar to the right to make a move. So what is the power required? Well, the power required is equal to work done over time, and the work done is equal to force times distance over time. And of course, distance over time, that's the same as velocity, so it would be equal to the force times the velocity. In this case, the force is 0.3686 newtons, and the velocity is 2 meters per second. And when we multiply that times 2 equals, we get 0.737 watts. So that's the power required to move the bar to the right. And if you take a look, you'll notice that the power required to move the bar to the right is exactly equal to the power consumed by the resistor, which is kind of interesting. So all of the power required to move the bar to the right to overcome the force in the bar, because the current running through the loop acting on the magnetic field causes the bar to be pushed to the left. So to overcome that force, all that power is consumed by the resistor in the circuit. And there's a very good example of how you work with Faraday's law and Lenz's law in this example. All right.